Okay, so hi everyone, I'm Pierre from Pisa, and today I'm gonna tell you about a new approach, okay, a Litecoin approach to compute to compute cosmological observables beyond linear order, and it's a kind of research I'm doing with Giuseppe Fanizzi and my supervisors Matteus and Giovanni Marozzi. So we know that we are entering the era of precision cosmology, meaning that we are about to receive an unprecedented amount of high precision data from large-scale cosmological surveys. And these, represent new opportunities, but also challenges, because then our theoretical predictions should be as accurate as the level of precision set by cosmic surveys. And we also know, as a kind of motivation for this work, that in phenomena which are responsible for the formation of structures in the universe, many linear effects come into play, like couplings of linear modes between each other, and relativistic effects as light cone distortions, frame dragging, redshift space distortions, and so on. And all of this is going to have an impact on the large-scale structure cosmological observables, which is why we really need a powerful tool, to compute them to higher orders in perturbation theory. And a possible way of doing that is to resort to the geodesy Litecoin coordinates. So let me recall briefly how they are introduced. So we agree that light rays propagate on the past Litecoin of a given observer, and that cosmological observations are made on your past Litecoin, which is why we search for a kind of physically motivated or observations-oriented set of coordinates. So in this cartoon, just to get an idea of what's going on, okay, suppose you are looking at a fish in the sea, and we know that because of refraction effect, the measured position of the sea, of the fish in the sea is going to be different from the real position occupied by the fish. Suppose your fish is the source, then the angles of the source are different from the angles you measured. And this is why, in general, we don't use a frame which is adapted to how light rays propagate, and they do that on the past Litecoin of the observer. So in this gauge in particular, if you use GLC coordinates, all the effects of distortions are already incorporated into the geometrical formalism you are using, okay? And the key property of this gauge is that the angles at the source, so the real angle occupied in the sky by not the fish but the star, will be exactly the same upon your request of the angles that your observational angles, okay? And mathematically, the way to achieve this is to use these coordinates Matteus has introduced. So tau is such that the level sets define a free-falling observer. Then you trivialize the expression of the Litecoin to the level sets of a null coordinate, so the most simple expression you can have. And then, okay, inside this Litecoin, photons propagate with constant values of the angles. So they are kept constant along the photon propagation direction along the line of sight. And it turns out that, as people have done, is a kind of bottom-up approach in this paper. The only metric which is compatible with this kind of requirement is the GLC gauge, where epsilon and UA are some given functions of space-time coordinates, and gamma B is the induced metric on the space given by the intersection between these two hypersurfaces. And you can prove that this is diffeomorphic to a two-sphere parameterized with your angles. And with a kind of more observative approach, okay, here we are just, so first point, we are considering the fact that light-like geodesics are exactly solved at any order in perturbation theory by this simple expression. So this metric here knows, let's say, knows nothing about what is background and full linear formula. It has a full linear behavior, and you produce this kind of non-perturbative solutions. And to identify a given source in the sky in terms of this observational approach, you have the redshift, and the redshift, the first kind of cosmological observable, admitting a neat and non-linear expression in terms of GLC metric to just the ratio at the observer and at the source of the epsilon function. And then the angles stress, again, that they are demanded to be the observational angles. Now, we want to work in perturbation theory. So the approach is the following. You take the flat FRW geometry G bar, and you perform a background diffeomorphism to move to a background metric, which is a metric adapted to a Litecoin foliation of spacetime. And on top of this, you add first and second order perturbations. So you're going to have scalars, vectors, and tensors up to the second order. And then the key point, mathematically but also physically, of this formalism is that this diagram commutes. So let me explain what I mean. So you take a given gauge in standard perturbation theory, and you can move from one gauge to another using the usual usual gauge transformation. So you pick one first and second order gauge fields, and then you can perform the passive way of transforming spacetime to move to a given gauge on the light cone. But if you follow these, these arrows, this flow, you are going to have the same kind of result that you would have following these two kind of arrows. So before you move to the light cone, and then you consider a gauge transformation inside the light cone, which is why we have computed first and second order gauge transformations of all the functions arising in this perturbed light cone geometry. And a nice point here is that by means of this diagram, you can produce non-perturbative formulae that connect standard perturbations and light cone perturbations, because in this kind of diffeomorphism, the perturbations are only encoded in the metric tensor, so the Jacobian only contains the background relations here. Okay, so let me stress again the key advantages of using such a gauge. Okay, they are twofold. On a non-perturbative framework, you can produce, as for the redshift, fully nonlinear formulae for your cosmological observables you are interested in. And on the non-perturbative, in a non-perturbative regime, the nice thing is that observables are factorized as products of perturbations, which are just evaluated at the initial point, so the source position, and at the observer position, at the final point. So you get rid of nested integrals along the line of sight. And let me stress once again that this is due to the key fact valid in the GLC gauge that observer and source are connected by means of theta constant geodesics, which are living on a W equal constant past light cone associated with a free-falling observer. So second kind of cosmological observables we are computing is the angular distance redshift relation. So we know that in general it is connected to the determinant of the Jacobi map, which is a way of relating an observer to a source, accounting for deviations effect geodesics are subject to because of the curvature of spacetime, so because of GR. And what's nice is that in GLC gauge, the Jacobi map admits a very simple non-perturbative formula in terms of the determinant of the gamma B matrix I have introduced so far, so the induced metric on the intersection between a tau equal constant hypersurface and the past light cone of your geodesic observer. Thank you. And so what we do in our approach is following a gauge invariant formalism, and we express the final result for the angular distance in terms of the gauge invariant variables for each perturbations. So you take this formula, you expand this formula in perturbation theory. Sorry, I'm just going bad. You take this formula here and you expand in perturbation theory after having fixed the GLC gauge at a fully nonlinear order. And to do that, you have to find relations at a perturbative level to fix the light cone gauge. And so, in this way, the main results of our paper we are about to publish are these two, maybe. So, first one is that with a kind of kinematical approach, you are able to remove annoying infrared divergences associated at the observer with the observer position, and you can do that in a totally model independent way, just with the geometrical approach as Matteo has stressed so far. And the second result is that our results are expressed, typically results are expressed in a Poisson gauge or generalization of the Newtonian gauge. In our case, the standard counterpart of the GLC gauge has been dubbed the observational synchronous gauge, which is the gauge we are presenting our results. And as in the standard synchronous gauge, the free-falling observer is measuring an unperturbed time. But here we are adding the extra request that the angles are the observational angles, so the directions of observations in the sky. And these are the results for the first order angular distance, where you can recognize the usual effects, Sachs-Wolf, lengthening, and so on. And these are the extra terms at the observer at the first order that make your angular distance the one measured by a free-falling observer, as in this gauge. And so to conclude, we have obtained the analogous of the first order angular distance, second order, kind of 2 pages of formula. And we are including GR effects. And our forthcoming project is devoted to other cosmological observables like the redshift drift, after having validated our formalism thanks to a thanks to a cross-checking of our formula for purely source contributions. Thanks. So thank you. If you want to think in terms of Barty potentials, yeah, it's non-perturbative in the sense that, let's come back to the GLC gauge. What's going on? Okay. So when you write down this metric here, you are not thinking about what is the background and which kind of perturbations you are adding on top of this background. And so when I mean, yeah, this is a fully nonlinear formula, which is you are not yet distinguishing what is first and second order and so on. Instead, when you work in perturbation theory, then you do that, and you can compare, the light cone fully nonlinear GLC metric with this metric here, and then you can get the perturbative counterparts of epsilon at the first order and at the second order. So the formalism is helpful because you can you can skip the part where you compute solutions to geodesic equations and equation of motion, because they are simply provided by this kind of equations. But then, since the universe is perturbative, you work in perturbation theory and you compare the two approaches. But you are relying on a light conformation which is valid at any order, and this is so helpful in going beyond linear order because of this kind of formalism. Yes. Yeah.
Yeah, so there is a classical formalism to compute the under account the spectrum of the GR correction by component
Mm-hmm.
the class. And from what I understand, the difference that we do is just when we did forecasts using the Bomber formalism for some futuristic survey, we found that most of the GR correction are completely detectable. Are these new terms that you found that it could be more detectable than
At the moment, I'm not totally sure, but I think that what we should do is like to take, as they did for the angular distance, also Giovanni did, for example, you should take the final formula at first order, compute and correlation functions numerically, and see how, in terms of numbers, how much this effect is relevant. We expect they are small, sure, but they must be accounted for if you want to use this kind of observative approach. So it's a work in progress. I mean, we should apply this. Our forthcoming project should be devoted also to numerical calculations.
Different case we have about what can be done with
Yes, thank you. Hi, everyone. My name is Kate Story-Fisher. I'm a postdoc at Stanford KaiPak, and I will be talking to you today about simulation-based inference from galaxy clustering with our library called Muchísimox. Someone in this room was trying to recall my talk title and dubbed it so many sims, like a lot of sims. So that's what I'll be telling you today about what you can do when you kind of get around this limitation of simulation-based inference. So a quick recap of the topic. So often when we do inference from galaxy clustering, we're doing a likelihood-based inference. And when you do this, you have a prior and you define some likelihood that you have to typically assume is Gaussian. And then you run a sampler based on your observational data and compare it to your model at every step, and from that build up your posterior. And because of these restrictions, we typically require that the data in this case that we're using is a summary statistic. So the power spectrum, for example. But it's hard in this framework to model higher order statistics that we need really good theory for. And it's also hard to understand how the plethora of systematics we have might affect these especially higher order statistics. So an alternative that we heard a little bit about from Urosh earlier is simulation-based inference. So the diagram looks a little different